Hi and welcome to this second video about the preparation of benzonitriles. In this video we'll have a look at the conversion of anilines first into diazonium salts and then into benzonitriles. Anilines are readily available, for instance by reduction of nitroarenes, and strong acids and sodium nitrite are also inexpensive. Unfortunately, the cyanation of diazonium salts is not an easy reaction and many things can go wrong. I will therefore show you many examples to highlight potential problems and hopefully provide you with suitable conditions for your specific target compound. The first step of these reactions is the diazotation, which requires strong acids and can therefore not usually be conducted in the presence of cyanide. Diazonium salt formation is a fast reaction and can be run like a titration just before the cyanation step. Only the fraction of unprotonated aniline can be nitrosated, but this is a fast reaction and will be complete for most anilines in seconds, even with an excess of a strong acid. Sulfuric, hydrochloric and tetrafluoroboric acids are most commonly used and are required for the protonation of nitrite and for the dehydration of the tautomerized N-nitrosoaniline. This last step is reversible, however, and neutralization or the addition of nucleophiles can cause the formation of various azo compounds. Because these are colored, the end of a diazotation can be recognized by the bleaching of the reaction mixture. According to the stoichiometry of diazotations, 2 equivalents of acid will be consumed, and more than 2 equivalents will usually be needed to stabilize the diazonium salt. Some chemists add urea to the finished diazonium salt to destroy the excess nitrite, but this is only necessary if nitrite severely inhibits the next step, what is almost never the case. Low molecular weight diazonium salts should not be isolated because these can explode unpredictably. These explosions usually start by a single electron transfer from the anion to the diazonium cation, and the explosiveness of diazonium salts therefore increases when the anion becomes more easy to oxidize. Particularly stable are tetrafluoroborates, sulfonyluimides or bisulfates, but even these salts sometimes explode. Ideally, these intermediates are generated just before use and kept in solution. The less basic the aniline, the more difficult becomes the last dehydration step. Diazotation of nitroanilines, for instance, will require more and stronger acids than alkyl or alkoxyanilines. The diazonium group is strongly electrophilic and sterically highly accessible. Michael and other additions to the diazonium group are therefore fast reactions. All kinds of nucleophiles can add, including water, and diazonium solutions are therefore only stable when kept acidic. The cyanation is usually performed by adding a cold aqueous solution of the diazonium salt to a freshly prepared cold aqueous solution of an excess of copper cyanide. Thereby a yellow oil precipitates, which probably is a diacenyl complex of copper. To prevent foaming and the accumulation of larger quantities of this explosive oil, toluene or ethyl acetate should be added, and the biphasic reaction mixture should be vigorously stirred to provide for a good dispersion of this oil. One possible mechanism of cyanation is the homolytic fragmentation of this complex, followed by nitrogen release and formation of an aryl radical. This radical would add to the excess copper cyanide to yield the benzonitrile and elemental copper. The initial step of the reaction is a reduction of the diazonium salt by copper cyanide, and the resulting copper-2 can reoxidize the elemental copper to copper-1. One alternative mechanism could be an intramolecular, concerted aromatic substitution, as sketched here. For some copper-mediated reactions of diazonium salts, however, there is solid evidence of the formation of aryl radicals as intermediates. Some examples have also been reported of the use of only catalytic copper cyanide in combination with an excess of sodium or potassium cyanide to bring about this cyanation. Here the mechanism would be slightly different. An excess of cyanide will enhance the solubility of copper cyanide by converting it into an anionic dicyanocopper complex. This complex can reduce the diazonium cation and cause the formation of an aryl radical, which can then add to a copper-bound cyano group. The resulting intermediate can fragment into the benzonitrile and copper 0. The copper 2 cyanide formed by oxidation of copper 1 is not stable and decomposes into cyanogen and copper 1 cyanide. Alternatively, it can oxidize the elemental copper to copper 1. The reason why cyanations with only catalytic quantities of copper cyanide do not usually work well is that the aryl radical does not add to ionic cyanide but only to copper-bound cyanide. If the concentration of copper cyanide is too low, the aryl radical will undergo other reactions and the yield of benzonitrile will drop. As mentioned, strong foaming can become a problem in these reactions, and a layer of some organic solvent may help to prevent the reaction mixture from creeping out of the reactor. I've had this problem a number of times, in Sandmeyer iodinations and during the preparation of phenols from anilines. There is an older JACS paper which recommends the neutralization of diazonium solutions prior to cyanation, in order to avoid the formation of gaseous hydrogen cyanide. This is, however, problematic because a higher pH can readily cause the formation of unreactive diazoates. Under basic conditions, ionic cyanide will also add to the diazonium group to yield stable azocyanides. Thus, a better strategy is to slowly add the cold, acidic diazonium salt solution to a warm solution of copper cyanide or mixtures of copper and sodium cyanide. I'll show you now some specific examples, so you get an idea of the scope and the required conditions for these reactions. Here, a 3-aminopyridine was converted first into diazonium chloride and then into nitrile in the way I just told you, by adding the diazonium solution to an excess of freshly generated copper cyanide. A high yield of the target nitrile was obtained. More problematic are starting anilines that contain other functional groups which can be nitrosated. These include alcohols, amides, and primary or secondary amines. In this case, the starting material also contained an imide, but still the expected nitrile could be obtained in 52% yield, despite the excess of nitrite. Here, the diazotation was conducted with acetic acid, not a very robust strategy, but sometimes it works. By the way, diazotations usually proceed quantitatively, and only a very slight excess of nitrite should be used, something like 1 to 5%. In this example, the excess of nitrite was way too large, what probably contributed to the low yield. Indoles can be nitrosated at nitrogen, but successful examples of the cyanation of unprotected amino-indoles have been reported. Here, for instance, the desired nitrile was obtained in 46% yield after nitrosation with an excess of terz-butyl nitrite and cyanation with copper cyanide. Again, the excess of nitrite was too large. In this example, the diazonium chloride was generated from just one equivalent of sodium nitrite to avoid nitrosation of the acylguanidine substructure. Cyanation with an excess of copper cyanide gave a fair yield of the target nitrile. This is a standard diazotation cyanation procedure of a simple aniline with just one equivalent of copper cyanide. To prevent hydrogen cyanide formation, already the diazonium chloride solution was neutralized with sodium bicarbonate. I would rather have added the bicarbonate to the copper cyanide or simultaneously during the addition of the diazonium solution, to prevent additions to the diazonium cation. Anyway, the expected nitrile was obtained in high yield. Also, aminobenzoic acids can be cyanated this way, as shown here. With fluorinated anilines, one potential side reaction is aromatic nucleophilic substitution of fluoride by hydroxide or cyanide, because the diazonium group is strongly electron withdrawing and activates arenes to undergo such substitutions. This was not a significant problem here, though. Even thiocyanates can remain unchanged during cyanation of an aniline. In this example, the aniline hydrochloride was nitrosated with just one equivalent of sodium nitrite in aqueous acetic acid. Addition of the resulting solution to freshly prepared copper cyanide gave a high yield of the target nitrile. The copper cyanide solution was prepared as usual from copper sulfate and an excess of sodium cyanide. As a byproduct of the reduction of copper 2 to copper 1, cyanogen is usually formed. To increase the solubility of copper cyanide in water, ammonia was added in this instance. Alternatively, excess sodium cyanide also usually increases the solubility by formation of an anionic dicyano-copper-1 complex. Particularly difficult starting materials are anilines containing a primary or secondary aliphatic amine. An excess of a strong acid may protect such amines from nitrosation to some extent, but not completely, and a better choice would be protection as a carbamate. In this example, such an aminoaniline was converted into diazonium chloride with just one equivalent of sodium nitride, and then cyanated with potassium cyanide and one equivalent of nickel sulfate. The target product had to be purified twice and was obtained in only 33% yield. Cyanations with only catalytic amounts of transition metals do not usually work well and might require a lot of optimization and other additives. Here, a diazonium tetrafluoroborate was cyanated in high yield with only 20% of copper complexes under anhydrous conditions. More realistic is the strategy used in this example. Here, an aniline was first diazotated in acetic acid with a slight excess of nitrosyl sulfuric acid. This inexpensive reagent has the advantage of not generating any alkali metal waste. The diazonium solution was then added slowly to a concentrated aqueous solution of sodium cyanide containing only 10% of copper cyanide. Aqueous sodium carbonate was added simultaneously to prevent acidification of the reaction mixture. The target benzonitrile was obtained in 80% yield and only relatively little waste was generated if compared to the previous examples. Another alternative is the use of trimethylsilyl cyanide as a cyanide source, together with substoichiometric quantities of copper oxide. These conditions enable cyanations to be conducted under anhydrous conditions, as shown here. Recently, the surprising cyanation of diazonium sulfonyl imides was reported, which does not require any transition metal catalyst. According to the authors, the starting diazonium salts are stable and can be isolated and stored indefinitely. In their proposed mechanism, however, the sulfonyl imide anion reduced the diazonium cation by single electron transfer, just like copper cyanide would do in the standard Sandmeyer cyanations. I find this very surprising, because the thermal stability of diazonium sulfonyl imides suggests that the anion is not readily oxidized. Anyway, I hope that the authors characterized their products carefully. Under the reported conditions, I would expect that the main product would be an azocyanide, not a benzonitrile. What leads us to the discussion of potential side reactions. As mentioned at the beginning of this video and as shown here, when diazonium salts are treated with a cyanide, in the absence of copper or other transition metals, a quick addition of cyanide to the NN triple bond occurs. The resulting azocyanides are stable and will have NMR spectra that closely resemble those of benzonitriles. Even the mass spectra will be almost identical because most azo compounds readily lose nitrogen during ionization and do not give any M+ peak. Thus, only the melting point, elemental analysis, and UV or IR spectra would allow to distinguish between an azocyanide and a benzonitrile. Another typical byproduct of diazonium salt decompositions is the reduced arene. Diazonium salts are strong oxidants and can abstract hydride from alcohols, ethers, aliphatic amines, and other potential hydride donors. Here, for instance, the hydride source was probably the crown ether. Depending on the solvent, either the reduced arene or an azocyanide were obtained, but I do not see any obvious reason for this solvent effect. Anyway, reductions can generally be suppressed by choosing solvents resistant toward oxidants, such as acetone, acetonitrile, acetic acid, or water. This here is an organic synthesis procedure for the reductive deamination of nitrotoluidine with ethanol. No copper was required, what suggests the mechanism to be hydride abstraction from ethanol. The mechanism of the reaction of diazonium salts with ethanol is complex and highly dependent on the substituents at the arene. One possibility is hydride abstraction, followed by homolytic or heterolytic fragmentation of the aryl diazine. The formation by other routes and decomposition of phenyldiazine has been studied in detail, and its main decomposition products are benzene and nitrogen. Alternatively, the reaction of ethanol with diazonium salts could be a radical chain reaction. An intermediate aryl radical could abstract a hydrogen atom from ethanol, and the new radical would reduce the starting diazonium salt to generate the aryl radical. It has been found that electron-deficient diazonium salts undergo reduction by ethanol in high yield, while electron-rich diazonium salts occasionally also yield ethers as byproducts, in particular with methanol and other alcohols that are difficult to oxidize, such as trichloroethanol. In this example, again an ether had been used as a solvent, what caused the formation of large amounts of benzophenone. A second byproduct was an aryl chloride. Aryl halides are also common byproducts of these reactions, especially if too little cyanide is used. This is an example of one-pot diazotation and cyanation conducted in DMSO. Nitrosation was brought about with terzbutyl nitride, directly in the presence of copper cyanide. The main byproduct was again a deaminated arene, and I would guess that the required hydrogen atom came from the terzbutyl group. An aryl chloride, a nitroarene, and a phenol were further byproducts. This here is an instance where a large amount of aryl chloride was formed during Sandmeyer cyanation, probably because of the use of copper-1 chloride as precursor to copper cyanide. With sulfuric acid and copper sulfate, this problem could have been avoided. Aryl radicals formed during these reactions can also add to electron-deficient alkenes and to other arenes. In this example, no copper cyanide, but only an excess of potassium hexacyanoferrate 2 was used to decompose the diazonium salt. Intramolecular biaryl formation was one of the main reaction pathways. Here are some further examples, but many more have been published. You can also find this reference list in the description of this video. The next video of this playlist is about the preparation of benzonitriles by amoxidation of toluenes, benzyl alcohols or benzyl chlorides. This is the most important approach for the industrial production of aliphatic and aromatic nitriles, but often requires special equipment not always available in standard laboratories. Nevertheless, in recent years a number of procedures were developed that are also suitable for laboratory preparations and for structurally complex benzonitriles. So don't miss it.